Good evening and welcome. Thank you for joining me after an exciting day of breakout sessions. A quick show of hands. Does anyone fear that your continuous delivery pipeline is going to break your production environment? I see some hands over here, over here as well. Well, if you do, you're not alone. This talk is about adding safety checks to your continuous delivery pipeline. I'm going to show you how to efficiently test your changes before pushing them to production, and how to add safety checks in the deployment process in the production portion of your pipeline. Hello, my name is Curtis Bray, and I own the continuous delivery tool AWS Code Pipeline. We're going to make our production pipeline safer by performing tests to block bad code changes before they reach production. We're going to improve monitoring of production so that you can identify production issues quickly. We're going to configure deployments so that our deployment engine only deploys changes safely. And lastly, we're going to modify the behavior of our pipeline so that we only deploy to production when it's safe to do so. Now, the techniques that we're going to use are leveraging automated testing to quickly identify regressions before they reach production. We're going to continuously test production to identify any functional regressions quickly. And we're going to validate running software on each host at deployment time. This ensures that our deployments are successful. Big bang deployments can be dangerous. So instead, what we want to do is segment production and deploy to each segment separately. And then when production is unwell, and we don't know why, we're going to halt promotions into production to help stabilize the environment. Now, key components to being successful at continuous delivery is to have an automated release process. This means you're using version control for your source code. You've automated your build and your deployment steps. You likely deployed them to more than one host. And you've also written unit tests and integration tests that you can rely on to capture regressions quickly. You've then tied this all together with either a homegrown script or an off-the-shelf product to create a pipeline. In addition, you've set up some operational dashboards so that you can monitor the health of your production environment. In the end, this means your automated process, your pipeline, would look something like this. So at a high level, this talk is focused on deployment and release automation best practices. The techniques I'm going to use should be transferable to whatever tools you're using today. That may mean you need to extend those tools, but that's all part of building out your continuous delivery pipeline. I believe that these practices are easier to understand when they're made concrete. So for this talk, I'm going to use our AWS tools to demonstrate each of the techniques. We're going to use 4 different categories of tools in this talk: monitoring, software development, build and test, and deployment tools. For monitoring, we want to be able to listen to production and have it send us alarms when things go bad. We're going to use CloudWatch for events, metrics, and alarms. We're going to extend our release process with some software development tools. In this case, SNS and Lambda are going to provide us with the tools we need to extend code pipelines' behavior. We'll use Code Build as our fully managed build service where we're going to be able to compile our code and run our tests, and then package it in a form that's ready for deployment. And lastly, we're going to use some deployment tools to ship our code into production. We'll be using code deploy to deploy onto our EC2 instances. And then we're going to use code pipeline as our continuous delivery service that's going to automate that end-to-end process. OK, now let's translate this abstract release process into code pipeline. Again, you should be able to translate this into whatever pipeline tools you're already using today. So you can see our 5 actions in our end-to-end release process map onto code pipeline like this. So a pipeline models our workflow from end to end. Within our pipeline, we can have stages. And you can think of stages as groups of actions. An action, or a plugin, is what acts upon the current revision that's moving through your pipeline. This is where the actual work happens in your pipeline. Stages can then be connected by transitions. And in our console, we represent these by an arrow between each stage. Transitions can be enabled or disabled. And when you disable a transition, that's how you can prevent changes from being promoted into production. Each time a new change is committed into your source location, a new pipeline run is triggered. This new code change then passes through all the actions in the pipeline. And many pipelines in the final stage, that's where a deployment to production happens. So our pipeline is configured to use code deploy. And we're going to use it to deploy to 3 hosts. The defaults in code deploy are to deploy to 1 host at a time. But we're going to modify this slide throughout the talk, and we're going to see how our techniques are going to change our release, our deployment, and our production environment. So now that we've got the prerequisites out of the way, let's move on to our first technique. But first, a quick story. So when your team writes software, there's bound to be tests that slip by local developer box testing. I remember a team in a situation where they needed to push out an urgent bug fix through their pipeline. As they got ready to push that change, they noticed that they'd been committing regular code changes for the last couple weeks, but none had actually been reaching production due to a failed integration test. The team was busy writing software, but lost sight of tracking that software all the way out to their production boxes. If the team had more proactive notifications of their test failures, then they would have had better hygiene of their pipeline and would have been more confident of making this urgent change, knowing that it was going to be the only thing being pushed to production at that time. So let's not be this guy. Let's make sure that we have reliable automated tests in a pre-production environment that doesn't slow down our release pipeline. The takeaway here is that although we're committing code, it doesn't mean our customers are getting that benefit if our continuous delivery pipeline is blocked. So some integration tests can take multiple hours or longer to run, so it's not realistic that the developers would sit there and manually watch for a success or failure from the test. So to solve this problem, we need to automate the notification of test failures, and we need to deliver it to a place where the developers live. And that would keep the test and the pipeline in good health. So for each build, the suite of unit tests should be run automatically. Once built, it would be deployed to a dedicated integration environment. The integration environment then can be used to test multiple software components together and to run other automated tests like UI testing. If any of those automated tests fail, the development team can be notified in their chat room immediately to rectify the issue. So let's look at how we can utilize code build as our container for building our software and running our automated test executions. Now, again, each commit of your source repository is going to trigger a source change. Then it'll be automatically built and unit tested, and the application will be deployed to your dedicated integration environment. At that point, additional integration and browser tests can be run in parallel against that integration environment. Now here's a screenshot of showing how to configure CloudWatch Events when a particular action fails in your pipeline. In the event source, we can select all code pipeline actions. Then we select the state of failed. We can then configure the failure event to trigger a Lambda function. Using that Lambda function, we'll then notify our Slack or our Chime chat rooms, and then CloudWatch can even allow you to further refine the filter down to a specific pipeline or specific action or action type. So now let's take a look at that from an end-to-end flow. The change enters our pipeline. It's built, unit tested, and deployed. But in this case, a failed UI test would then trigger a CloudWatch event. That event triggers our Lambda function that notifies the developer chat room. Now, it's important to know that every change that moves through the pipeline is going to send a unique notification if it failed. And each of those notifications would detail the exact change and action that failed. OK, that covers our first automated testing technique. Now, we all run complex systems, and they can often break in some unexpected ways. I remember a time where a team had a buy button disappear from their website. The site had some downstream dependencies on an inventory management system. And that system started returning empty pricing data, so the site simply stopped showing the button. The team was unaware of the issue until a customer actually contacted them and told them of the problem when they were trying to buy items. If the team had better information about the state of their service, they might have been able to fix the issue before the customer even discovered it. So the lesson to take away here is that although our service is working currently at one point in time, it doesn't guarantee that it won't stop working at a later point in time. There's a wide range of reasons this service may degrade, including dependency or environmental changes. These regressions in our service aren't caught with our standard monitoring. So, to solve this problem, we can use synthetic traffic to simulate real users and identify problems before the customers run into the issues. Our synthetic traffic needs to test all business-critical functionality. We want our synthetic tests to behave like real customers do. So this would typically mean you would authenticate, add an item to a cart, and check out. But it's important not to just test the user interface, but also the public APIs. The tests need to run quickly so that you get feedback fast. The longer the test runs, the more likely your customer is going to find the issue before you do. So a good target is to have your tests run in about a minute. Since we're simulating user interaction with our site, we can test the speed at which our calls return from the customer's perspective and tell if the customer experience is degrading. We can also test to see if our site is reachable by our customers. The system may be up, but for some reason, traffic from our customers may be blocked and not being received. All right, so let's look at the flow of how synthetic traffic works. When a customer uses our service, we return this successful result back to our customer and then report success to our monitoring system, in this case, CloudWatch. Our synthetic traffic has the same workflow. It makes a request to our service reports success to CloudWatch, but then our synthetic test also sends results back to our monitoring system. The synthetic traffic metric will let us know if this critical business functionality is no longer working. It provides us with data also to then measure the client latency and reachability. Now we're going to schedule these synthetic tests to happen once a minute with CloudWatch. When our synthetic test fails, then it will issue an alert and raise an alarm through CloudWatch. At that point, our operators can respond and fix the issue. Now, with this particular setup, we're not provisioning any new hosts into our fleet to run these tests. So why do we have two metric streams? It may not be obvious why both our service and our synthetic traffic tester both send the results to CloudWatch. So if we think back to that earlier story where the site no longer displayed the buy button, the customers will continue to use your website and be unable to see the buy button, but all the monitoring data from your service reports healthy because the customer interactions will work. However, from the synthetic testing point of view, a business-critical functionality is missing. So the synthetic tester will then report an error back to CloudWatch to trigger an alarm so the problem can be resolved. So now let's build out one of these synthetic traffic tests. We're going to build the synthetic test in Lambda and have it run every minute. In this example, we're not going to build a complex test that's going to simulate all customer interaction, but instead we're going to do something a little simpler. We're going to test that we can access the website by making an HTTP call and validate the contents of the response. We're going to use Lambda to run our tests, and then we'll use CloudWatch to capture the data from the test. The Lambda console has sample applications called blueprints, and these can help you get started building out functions very quickly. Lambda has a blueprint for synthetic tests that we're going to use in this case. Canaries are a term used by our internal teams at Amazon for a synthetic test, which is why we use the term canary here. Now, during the blueprint configuration, you can also select to invoke the Lambda function on a schedule with a CloudWatch event. Now, here's the Python code that's created by our Lambda blueprint. We're going to define the URL that we're going to test and the text that we're looking for, AWS code pipeline. The URL open method does the actual work of making the request to our site, and then the validate method looks for the text on the page. Now, it's very important to return the right status codes because those are what are fed to CloudWatch. If there's a failure, Lambda will raise an exception. Otherwise, it will exit normally. Lambda functions automatically report their health of each of their calls as CloudWatch metric streams. So in this screenshot, you can see a number of Lambda functions that have been created. And then I can graph the metrics that are important to me by selecting them in the console, and also build alarms off of those metrics. In this case, we want to build 2 alarms. One, if the synthetic test fails. And the other alarm would be when we're receiving no traffic, so for some reason the test isn't running. Now, if the Canary fails, our operator is going to get notification immediately. So the process to release and deploy changes isn't altered at all by the addition of these additional synthetic traffic, but it does provide us with valuable data on the health of our service, which we're going to use soon. Now, one of our teams had built an internal service, and they were getting ready to launch. An operations dashboard review is a standard process that we use when we're preparing to release a new service. In that review of the dashboard, we noticed that the service had been unavailable. And upon deeper inspection, we found out that during one of the deployments, a database table had been renamed. So the development team had fixed the table and redeployed and didn't think much of it. But during that deployment window, not one host in their fleet was serving traffic. They were completely down. The team wasn't checking whether their deployment had succeeded. They actually had a bug in their deployment process. So if this had happened a week later, it would have been much more catastrophic because the service would have been live. So let's look at how we can prevent this from happening to you in the future. Now again, we're using code deploy for all of our deployments here. Code deploy will deploy rolling updates to EC2 instances. As you can see, each host is taken out of the load balancer, the version is updated, and then it's placed back into the load balancer. But rolling deployments by themselves don't verify that the application is working when the instance is updated. This means if you accidentally made a change and your application stopped working, you could easily find your fleet broken and completely unable to serve traffic. So by default, deployment systems are unaware of application-specific logic, including whether the new code actually works. This means we don't know if the deployment has left our service running or whether it's broken. Rolling deployments need 3 checks for deployments to be safe. The first check we need to do is for each host that we deploy to, we should start up the application and then quickly verify that the application is working. Second, we need to configure our deployment engine to tolerate a small number of failures. And lastly, if the deployment fails, we need to roll back to the previous version. So let's look at how we can make these 3 changes in code deploy. Code deploy can be configured to run scripts at different parts of the deployment lifecycle. The AppSpec.yml file defines those lifecycles and the scripts to run. The lifecycle hook, the last one that we're interested in here, the validate service hook, is at the point where the application is started up and we can validate that it's running and return invalid results before adding it back into the load balancer. So let's look at our deployment process once we've added the deployment validation steps during our host updates. Now, when a deployment occurs and a host fails to start up, we'll fail the host deployment and not put it back into the load balancer. Now we fix the problem of only adding hosts back into service if they can serve traffic. But from a deployment perspective, it will have failed. And it's unlikely that we want to fail our entire deployment just because one host failed to start up. Imagine you run a large service and you have a fleet of hundreds of hosts. In this case, if a host fails to update, you want to quarantine that host and continue deploying to the rest of the fleet. In this example, we're also left with the fleet in an inconsistent state. So let's see how we can fix both of those issues. Now this is where code deploy's minimum healthy hosts can help us out. The minimum healthy host setting defines the percentage of hosts that must be healthy for a deployment to continue. Let's look at an example where we have a fleet of our 10 hosts, and we've set our minimum healthy host percentage to 70%. If one host fails their deployment, then the overall deployment will succeed. In this scenario, 90% of our hosts are healthy. However, if 4 hosts had failed their deployment, then the overall deployment would fail. In this scenario, only 60% of our hosts are healthy. But also notice that we have one host that wasn't deployed to because the deployment failed. Now, Code Deploy supports the minimum healthy host setting via deployment configuration. By default, Code Deploy will update one host at a time, but it also provides the ability to update all hosts at once or half at a time. If these options aren't suitable for you, then you can also define your own percentage via the CLI. So by using validation tests and minimum healthy hosts, we're going to prevent a large number of availability issues caused by bad code changes. But after a failed deployment, we still have part of the fleet running the old code and part of our fleet not in service. So Code Deploy will roll back to a previous application version if the deployment fails and the rollback option is selected. This should then restore your fleet to a healthy state. So managing deployment health doesn't affect our release process, but it does change our deployment process. After a host is updated, we need to test if the newly deployed code works. And to do this, we write tests to validate the running service. We can use minimum healthy hosts to allow a few hosts to fail our deployment and quarantine them for later. If the deployment breaches our minimum healthy host setting, then we're going to roll back and repair the fleet. Okay, next let's talk about segmenting production. So I remember a team, as part of their release process, they broke the ability to add items into the cart. The team had already implemented synthetic traffic testing, so they caught the issue very quickly, and they rolled back their change. Unfortunately, the service they broke received a lot of traffic. So customers were calling in and emailing and tweeting, frustrated that they couldn't add items. The service was only unavailable for a brief period of time, but it affected all of their customers. So let's not deploy in a manner that's going to impact every customer, even if that's what the grumpy cat wants you to do. If you leave production as one big pool, then any bad change can affect all customers. And that blast radius is just too large for many services. To reduce the risk of a bug impacting production, we can then segment our fleet into multiple smaller sections and deploy to one segment at a time. After each deployment, we can then run our post-deployment tests before we move on and deploy to the next segment. We keep deploying and testing until all of our production fleet is updated. So let's look at the different ways that we could segment production. The first step is to break your production environment down into multiple segments. And you can think of a segment as a deployment blast radius. So some typical segment types could first be a region. An AWS region is a physical location around the world where we cluster data centers, and we always segment deployments to at least a region level. We tend to deploy to one region at a time so that the blast radius for a change is limited to a single region. And we call each group of logical data centers an availability zone. And the zonal deployment pattern then allows us to tie software changes to network topologies. By deploying to a zone at a time, we can reduce the risk of a bad change affecting the entire region. But even a zone can be too large of a blast radius for many services. So we can create deployment segments that are subzonal. We see larger teams at AWS structure their deployments into subzonal cells. But all teams want to gain some confidence in their deployment before they start rolling it out into other segments. And these customers would deploy to a single host, a Canary deployment, before continuing out to the rest of their fleet. So here your release process changes to reflect the level of safety you want to achieve. The minimum configuration I see is one Canary deployment and then the deployment to the remainder of the region. A more common pattern is to deploy to 3 zones, each with 3 hosts. Having many hosts over many zones helps us with our availability because we can lose an entire availability zone and still have 66% of our hosts available to serve customer traffic. Now, to manage costs, we could migrate to smaller instance sizes. As we start deploying to production, we'll only deploy to one host, we'll validate that host in our post-deployment tests, and if all goes well, we'll start deploying our host to the next deployment group. If that first zonal deployment is successful, then we can perform our post-deployment tests and deploy to the remaining zones. So now let's model these different segments in code deploy. Code deploy uses deployment groups to group an application with hosts. A deployment group will identify the hosts based on their tag, their auto-scaling group, or both. This then allows us to specify the zone in which the host lives for an application. We can use these groups to identify both our Canary and our zonal-based deployments. So now let's take these deployment groups and add them into our pipeline. Our updated pipeline starts to look like this. We have each segment represented as a code deploy deployment group, followed by a test. You can see the Canary deployment, followed by the post-deployment test, and then the zonal deployment, followed by a post-deployment test, and finally, the deployment out to the remaining hosts. Now you'll notice that we don't make another validation in that final group. Since we're continuously testing production with our synthetic tests, an additional post-deployment test here wouldn't add any extra validation. So now let's get into the details of how to build one of these segments out and test them. So in order to test a deployment, we want to gather enough statistics about that deployment to gain the confidence that the deployment's good. Each call to our service is already writing success or failure information to CloudWatch. We can use that CloudWatch data stream as our data source to validate the segment deployment hasn't broken production. To ensure there's no larger operational issues occurring, we want to also look at our alarms and make sure nothing's firing. We're also going to time-bound our validation of that deployment. If we can't verify that the change is working within a couple hours, then it's probably not working. So we're going to time it out, and we'll use some code in order to do that timeout. Now we need to build a post-deployment test and add them into our pipeline. We could write these tests as a code pipeline test action, a Lambda invoke action, or a custom action. The good part about writing action is that they're easy to do, but the downside is they all have a 1-hour timeout. Our post-deployment tests could take many hours to run. So approvals have 7-day timeout, which is long enough to run our tests. Approvals are designed to pause our pipeline until an external check occurs. By default, they'll wait for a manual, they'll manually wait there for a human to approve the action. But they could also be configured to be approved via an API call. And that's how we're going to use them in this example. So let's take a look at the approval pattern. Now, approvals actions don't run code, but they can signal that they're waiting for an approval. An approval can be configured to send out a message on an SNS topic when work needs to be done. And then a callback can be made back into code pipeline to approve the action, and then the pipeline will continue processing the change. So let's see how to configure the approval and the SNS, configure the approval to use an SNS topic. In this screenshot, the approval action is being configured, and we're going to configure it to send this message on an SNS topic. Approvals also have a comment field, and the comment field can be used to pass additional machine data to the approver. In this case, the approver is a Lambda function, so we're going to send the data as a JSON format. We're going to pass through the CloudWatch metric stream that we want to monitor, the number of data points that are needed to succeed, and then a timeout period before we fail the test if we don't receive a positive result. So let's look at that end-to-end flow now of performing the test. When a change enters our pipeline, it reaches the approval action, and it sends a message on the SNS topic to our Lambda function. The Lambda function will then store the message in a DynamoDB table, and then we have a second Lambda function that will read that segment deployment approval data from DynamoDB. We use CloudWatch Events to schedule the calling of that Lambda function each minute. If we have enough data from CloudWatch, then we can call back into code pipeline and approve the action. That then allows our change to move on to the next deployment. Now let's look at each of these Lambda functions in a little more detail. First is the register deploy test function. Its goal is to read the approval data from SNS and write it into Dynamo. This function takes in 3 parameters. The first parameter, events, contains the information about the approval action that's been delivered from SNS. We'll pull out the approval information and put it into our notification data variable. In this example, we're just assuming one record, but in actuality, you could have many messages. Once we pull the data out, we can then write it straight into DynamoDB. Now let's look at the evaluate deploy function. It will allow a deployment to succeed if it can gather enough data usage points from CloudWatch. And it's going to fail the deployment if the tests take too long or if there's an alarm firing. I'm not going to show you the details of that code for that particular post-deployment test, although it's going to be available on our GitHub repository after the talk. Instead, I'm going to focus on the code to send the approval result back to code pipeline. Now, to signal code pipeline that a post-deployment test has succeeded, we'll call the put approval result method. This method requires the pipeline, the stage, and the action name to identify the action to approve. The method also requires a status and a message to signify that the post-deployment test is approved. So I want to briefly talk about Canary deployments because they're configured slightly differently than regular deployments. The way they're the same is that they are part of the production fleet, just like regular deployments, and they serve production traffic to customers. They're configured in the same way as the remainder of your production fleet. They participate in the production fleet metric stream and alarms as well. But where they differ is that they have their own metric stream to alarm on. Canary deployments emit their metrics twice, once for the production fleet and a second time for use in testing their deployments. Canary deployments need their own metric stream because Canary metrics can get drowned out when aggregated with the production fleet metrics. Think about the instance when you have hundreds of hosts in your fleet and you have an alarm configured to fire on a set of 3 failed data points, 3 consecutive failed data points. If your canary is throwing errors, it's very unlikely that the alarm will fire, even though the Canary deployment is clearly unhealthy. So instead, Canary deployments should emit a second metric, and the validation should occur on that Canary deployment metric stream. So segmenting our deployment has a big impact both on our release process and our deployment process. At a minimum, we'll end up with 2 deployments, a Canary deployment and a regional deployment. The extra deployment steps need to be reflected in our pipeline. Larger services may also choose to deploy zonally, and then we'll also add in our post-deployment tests to our pipeline. So now let's look at our last technique, halting promotions. At AWS, we regularly review internal availability incidents to identify their root causes. During a review of a new HR system, a customer had a bad host that was causing errors to be thrown, and so they took it out of the load balancer. Unfortunately, their pipeline pushed a new change that ran a script and put that host back into the load balancer. And now it began serving customer traffic again. So this was a bad user experience, or a bad customer experience, because the customer had random failures if they were hitting that host, but it also made it very hard for the operator to diagnose the issue that was occurring. So when your system is experiencing an availability event, it's helpful to keep the system stable. We want to disable new transitions into our production stages during an availability event unless we have a specific fix that we want to get out to production. So to do this, we're going to use promotion blockers. When your system is suffering from an availability event, there should be an alarm firing somewhere. Now this could be a service level alarm or a company-wide alarm. Service level alarms are owned by each team and fire when some portion of their service is not working. Company-wide alarms fire when a significant portion of your business functionality is broken. At AWS, when either of these alarms are firing, many teams halt promotions into production. So we've already built canaries that fire service level alarms when our service is in an unhealthy state. We can then wire that to a Lambda function and to a CloudWatch alarm via an SNS topic. In the Lambda function, we can then call back into our continuous delivery system and disable the transition into production. Now, disabling the transition is going to halt any changes flowing out into production. And this then gives us the operator the stability they need to diagnose the issue and resolve it. The operator can then manually re-enable the transition when the issue is resolved, and changes will continue to flow. The code to disable a code pipeline transition is fairly trivial. Code pipeline has an API named disable stage transition. Now this is going to then stop our change from entering production. We need to, though, scope this by passing in the pipeline name, the stage name, and whether we're disabling the inbound or outbound transition, and also provide a reason. When a stage is disabled, either through the API call or through the console, it'll contain a reason, and the operator can then come back and enable the transition once the operational event is resolved. Now, our release process is updated to disable promotions to production. As you can see, we're starting to build a release process that's able to adapt to environmental changes. So this actually finishes our review of the 5 techniques to improve your deployment safety. My goal was to teach you a few techniques to make your pipeline safer, and I hope these techniques will help make your customers happier and your operators happier as well. But this wasn't just a talk about handling a bad code change before it reaches production or modifying your release process, but it was about modifying your release process and your tools to behave the way that work well for your team. So to recap, we can use automated testing to quickly notify our developers and keep our pipelines unblocked and current. We can use continuous production testing to react quickly to production issues. We can deploy safely to production by setting up our deployment configuration to test each host after it's updated and roll back if the deployment fails. We also learned how to partition production by building Canary Deployments and zonal deployments. And then we wrapped up with the technique to manage our pipeline by automatically halting deployment production to production by disabling our stage transitions. So we've dramatically overhauled our release and our deployment process. We now have real-time data on the health of our system by adding in synthetic tests. From a deployment perspective, we've added in 3 new tests that didn't exist before we started. We're testing that each host conserves traffic, that each segment deployment doesn't create a functional regression, and we're testing whether deployment failed and triggering rollbacks if so. From a release perspective, we've added the ability to halt the flow of changes out to production during availability events. I hope you've learned something here today that you can then take home and apply into your own continuous delivery process. Thank you.